Okay, so today we will talk about sequences. Let me start by the definition. What is a sequence? So, definition. A sequence is a list of numbers written in a definite order. Okay, so like this: A1, A2, A3, 3 dot, AN, and actually it doesn't stop. So this is called the general term. You can use so the notation for a sequence. We can use notation, so like a set. We will use this notation, or if we want to precise from which index it is actually starting, you can precise this here. The n will be here, or in this example, greater than 1. So sometimes it can start at 0 or -1 or anything. But the important is that it's never ending. It's a list of numbers in a certain order, and it's never ending. Okay? Example of such sequences. Yeah, for example, you can you have. So what does it mean? This 1, okay? 1 will mean 1, 1, and forever 1. Okay? This is an example of sequence. Another example. So what would this mean? Okay, and here I precise. I will take from n greater or equal to 1. Okay, so I write in brackets a general term, and I deduce what is the sequence. So it starts by evaluating this, the general term, starting from n equal 1, isn't it? So it will be 1 over 2, so it starts by 1 over 2. What is the next term? Next term will be, as you see, 2 over 3, and then 3 over 4, etc. Okay. So this is this kind of sequence. You can have something more sophisticated, like you can consider cos n pi over, let's say, 6. Okay? And here you would start from n greater or equal to 0. So what is this? This sequence, so the first value is evaluated for n equals 0. So cos 0, you get, first value is 1, isn't it? And then the second one, you will get cos of pi over 6, which is, as you all know, square root of 3 over 2. And then you would have cos of pi over 3, which is a half. And then you would have cos of pi over 2, which is 0, etc. So you can, just by applying this formula, predict all terms of the sequence. It never stops. You can also sometimes define a sequence by a recipe, not by a single formula of the general term. This is a very famous example of such sequence, which is called the Fibonacci sequence, which is very, very famous from the Da Vinci Code, etc. So how is it defined? You define the first two terms. The f1 will be 1, and the f2 will be also 1. And then you define the next terms by a general formula implying the two last terms, namely the nth Fibonacci term will be equal to Fibonacci term n minus 1 plus Fibonacci term n minus 2. And this formula will be true for n is greater or equal to 3. So you have defined f1, f2, and then you get all the other terms by this equation. Okay, so you see you can define sequence by different things, by naming giving an expression of the general term or giving a recipe. Okay, now when you are given a function, you can study its so-called limit and also study if it's convergent or not convergent. I would like to define these terms. So a sequence an has the limit L, and we write limit of an when n goes to infinity is equal to L. Okay, so it's really a kind of limit. What does it mean? Yeah, or sometimes we will denote like this. I like this notation, it's very compact. Yeah, this is also nice. And this will happen if we can make the terms an as close to L as we like by taking n sufficiently large. In other words, so this is a kind of limit, and we can write it really mathematically. We are just asking that the following mathematical sentence will be true for any epsilon greater than 0. There exists some n, capital N, such that if n is larger than n, so this really transcribes the notion of limit at infinity. You can look at the previous definition of limits at infinity, it's precisely this. And then we adapt it. So what should happen? Well, the an minus L should become less than epsilon. Okay, so each time this limit exists, we say that an as a sequence is convergent when the limit does not exist. We say that the sequence an is, okay, so when it's not convergent, we will say that it is divergent. Okay, so this is just vocabulary. Convergent means that this sequence, this list of terms, when n goes to infinity, will approach some value, and we will call it convergent. And when we cannot do that, we will say that the sequence is just divergent. Okay, yeah, we can. Why don't we have a look at, for example, the first two, okay? So let's take the two first examples. Well, as you can see, the limit when n goes to infinity of 1, this is a constant. It can be taken as a constant function. So it will be 1. So this sequence is convergent. This is convergent. Now what happened for the next one? So the limit when n of n divided by n plus 1 when n goes to infinity. So yeah, how do we do that? Well, first of all, we observe that this n over n plus 1, we can rewrite it as follows. This can be written as n over n, and here I'm going to factorize. This is 1 plus 1 over n, isn't it? Right. Now, this I can cancel out. So this becomes just a function 1 over 1 plus 1 over n. Now, what happens to, I can calculate this now, okay? So this, when n goes to large n, will goes to 0 here, okay? So we will get 1 over 1, we get 1, okay? So both sequences are convergent. So we also get that n plus 1 is also convergent. That's right. Okay. Now let's see some theorem. So because it's very near, as you can see, it's very near the notion of limits. Okay, and we have done quite a lot of job concerning limits. So let's use what we know about limits to deduce something on the convergence or divergence of a sequence. We have the following theorem. So let's call it theorem 1. If we have a function f which admits a limit when x goes to infinity, let's say that this limit is L, and assume that our sequence is defined as the evaluation at n of the same function, then an is converging to L. Okay? So you can see basically convergence of sequences as a problem of limit at infinity of function. That's the really meaning of this theorem. Well, it's quite obvious to prove, so let's give another definition. We say that a sequence diverges, but diverges to infinity. Okay, so it's a kind of fact that it's divergent, but for some reason it's diverged to infinity. What does it mean? If an becomes large as n becomes large. And we write an goes to infinity when n goes to infinity. This is equivalent to say that for any m greater than 0, there exists a n greater than 0, such that if my small n is larger than capital N, so n large enough, then my an is also larger than anything, this capital N. Okay, so when we have this is a special case of divergence, and it's called divergence to infinity. Okay, example of this is, consider this function. Typically, when n goes to infinity, then the general term, which is n, also becomes infinite. So this is diverges to infinity, obviously. Now, this doesn't represent all cases of divergence. Okay, there is another case where a sequence will diverge. If you remember, convergence means that we have a limit, and that this limit is finite. Okay, is a finite number, real number L. Now, sometimes limits do not exist, and let's take this example, -1 to the n. As you can see, if you take n very large, well, the actual value of this will stay very small. It will be basically, this will be basically -1 or 1, but it will depend on the fact that n is even or odd, okay? So it doesn't converge to anything. It alternates between two values forever, -1 and 1, -1 and 1. It oscillates. This is a case where this is divergent. It's divergent. Definitely, the limit does not exist because it's alternately -1 and 1, but not diverging to infinity. So basically, you will have these two cases of divergence for sequences. Either the function does not exist or the limit is infinite. Okay. Now, as we have seen, sequences, the limit of sequences is based on limits of functions most of the case. Therefore, it's very natural that we will have also limit laws for sequences. And they are basically the copy and paste of the analog for functions, limit laws for sequences. So I will just give the statements. So here I will consider two sequences, A, N, B, N, and I will assume that they are convergent, very important sequences. And we will also consider C, some constant, a real number. Okay, given this data, then we have the sum and subtraction of limits. So limits of an plus or minus bn. This will behave exactly as the similar law for the function, and therefore it will be the plus or minus of the limits. Alright. Now you have the law of a constant times a sequence. So what is C times an? The limit of that is not surprisingly C times the limit of an. Another law is a product law. What is the limit when n goes to infinity of an, bn? And again, not surprisingly, this will be the product of the limits. Therefore, the limits of an when n goes to infinity times the limit when n goes to infinity of bn. Yeah, what about the power functions? So if I consider the limit of an to some power p, then this will be the power p of the limit. Okay, very nice and easy. Here I assume, however, that the power is positive and also that the general terms are positive. Otherwise, I have to be a little more careful. We have to distinguish several cases. So, okay, so we have this kind of laws. Well, we have also the quotient law. So this quotient law works same. So quotient law quotient. So if we have limit of an divided by bn, and of course we will assume that bn is not converging to 0, right? Then we can get that this is the limit of the sequence an divided by the limit of the sequence bn. Quotient law. Any other law? Yeah, basically you can do that for any laws for the limits and adapt it to the sequence. Now, another very important way, if you remember, that we had to calculate limits for a function was not only the limit laws, sometimes they are not enough, but we have the so-called squeeze theorem. So let's state this theorem. It holds also for sequences. So this is a squeeze theorem for sequences. It works perfectly, and it works like this. So if we have an less than bn less than cn, so this inequality, we are interested at what happens when n goes to infinity. So this just needs to hold for n large enough. We don't care if it's not true at the beginning, because we care what happens when n goes to infinity. So if we have this and an and cn are converging to the same limit L, then we can definitely deduce that bn will also converge to this L. Okay, so this works exactly as the case of function. Let's call this theorem 2. Okay? So what was theorem 1? Theorem 1 was that if the general term is defined by a function, then the limit of the sequence will be precisely the evaluation, the same limit as the function. Okay, this was theorem 1. Theorem 2 is the usual squeeze theorem. And theorem 3 is very useful, especially concerning the term, the sequences with term like -1 to the power n that are a little tricky to deal with. So we have the following result. If the limit of the absolute value of an when n goes to infinity is 0, okay, not any value but 0, then we can be sure that the limit when an when n goes to infinity will be also 0. Okay? Yeah, so this theorem is very useful. Let's see some example of calculation of limits using these results. Okay, so examples. Imagine that we have the sequence an equal minus 1 to the power n divided by n. Okay? Now, you want to study the convergence of this. Here it's a little difficult because to apply, for example, quotient laws, because this is not convergent. This is not convergent. The denominator is not convergent, as you can see. This is convergent. It goes to infinity. Okay, so we know the limit, but here the limit does not exist. So we are not in the hypothesis of the theorem. Okay, because the theorem needs both numerator and denominator to be convergent. This is not the case here. So we cannot apply the limit laws. And also, squeeze theorem here is definitely not the best method, especially when we have theorem 3. Okay, so let's have a look at theorem 3. We take the absolute value of that. Okay, so what is the absolute value of that? Well, this is easy. This is just 1 over n. And this definitely converges to 0 when n goes to 0. Therefore, by theorem 3, here we can conclude. Okay, we can conclude that this is converging to 0. Okay? Yeah, we will see many examples or exercises, so I'm not going to give too much example here, but I want just to study a very special case, which is a little difficult to treat by yourself. So this is the case of, so example, let's say this is 1, and then let's treat example 2. Example 2, we are going to consider the following sequence. an will be equal to r to some power n, and r will be some real number. Okay? Yeah, so we want to study the convergence of this limit, and here we really need to distinguish cases basically with respect to r. Okay? So the first cases we can consider is when r is greater than 1. So when r is greater than 1, what do we know about the function r to the x? So, of course, we know that when x goes to infinity, this goes to infinity as long as r is greater than 1, isn't it? So, we can say for sure that here we just apply theorem 1, actually, and we will get that the sequence r to the n will also diverge to infinity when n goes to infinity. Okay? This is in the case r greater than 1. Now, in the case where r is between these two values, 0 and 1. So here, the function will actually converge to 0 in such case when x goes to infinity. And we can also deduce from theorem 1 for the same reason that r to the n will converge this time to 0 when n goes to infinity. Yeah, so this is diverging to infinity, this is converging to the value 0. What happens for r equal 1? Okay? So let's consider the limit of this interval. For r equal 1, well, obviously r to the n in this case will be the constant function 1, isn't it? And we have seen that this converges to 1 when n goes to infinity. Okay? So it's converging. What happens when r equals 0 this time? So r to the power n is in this case 0, right? And therefore we can also deduce that r to the n is converging to 0 when n goes to infinity in such case. So both cases r equal 1 and 0 are converging cases. Now I want to treat the case where r is less than 0, so negative, and less than -1. Okay, so in this case, basically the limit when r, let's take the absolute value of it, right? This will be the limit of absolute value of r to the n, and here I will be less than 1, right? This value will be less than 1. So when n goes to infinity, as you know, this goes to 0. So here I will use theorem 3, which tells me that the same is true without taking the absolute value. So we will then use that the limit of r to the n when n goes to infinity will be also 0. Okay? Okay, so finally I just need to study the last case. So the last case is r less or equal to minus infinity. Yeah, maybe I should distinguish. Maybe I will take just less than minus 1, okay, strictly. Then this is diverging to minus infinity. And finally, the last case, when r is equal to minus 1, then as you can see, we will r to the n will oscillate between the two values, so it will be is divergent, but not to infinity. It's divergent, because the limit does not exist. Okay, so let's summarize all these results. Okay, so as a summary, we can see that this sequence r to the n is convergent. In which cases? Well, it's convergent if r belongs to, so the open interval minus 1 and until 1, then this will be convergent. And it will be divergent otherwise. Okay. And okay, when it's convergent, the limit will be zero. So it will be 0 if r belongs to the open interval minus 1, 1, and it will be 1 if r equal 1. Okay. So we only have two cases, these two cases. That's right. Okay. Now, another thing that we can use to study the convergence of the function is to study the property, is the sequence increasing or decreasing, etc., etc. So these are very interesting phenomena also for sequences. Let's recall some definition. Okay, so a sequence an is called increasing respectively decreasing. So what does it mean to be increasing? It means that the term, general term n, is strictly less than the general term an plus 1. And what happens for decreasing? Well, the opposite will happen. So respectively, we will have an greater than an plus 1. A sequence is called monotonic. Monotonic if it is either decreasing or increasing. So be careful that not every sequences are increasing or decreasing or monotonic. For example, -1 to the power n, as we have seen, oscillate between two values, -1 and 1. So it's sometimes increasing, sometimes decreasing. And therefore, this is definitely not monotonic. Monotonic. Now, what could be monotonic? Well, for example, this one is increasing, always increasing, and therefore, this is monotonic. Now, sorry, yeah. So, as a sequence, maybe I should write like this. Sometimes some people use round bracket actually, but yeah, this year we have to choose one, so let's choose these brackets of sets to design to represent sequences. So this one 1/n is decreasing. And also monotonic. All right. Now we have another notion for sequences, and this notion is a notion of boundedness. So let me explain what does it mean. So I need these two notions of monotonic and bounded to say more on the conversions of the function. So definition 2, let's say, this was definition 1. A sequence is bounded above if there exists some real number, capital M, such that if my AN terms are less, well, there will be less than capital M, and this will be true for any n. Bounded above, after this. So you have inequality like this. Below, you will have an inequality on this side, below. So a sequence is bounded below if there exists this time a small m in R such that an, so small m is less than a n for any n greater than 1. Okay, this is bounded above and bounded below. A sequence is bounded if it is bounded above and below. Okay, so you have three notions. Bounded above, so there is some value bigger than anything, and bounded below, the sequence is less than some small value, small m, and bounded means that any general term can be put in some interval, small m, capital M. Okay. Let's take some examples. Okay, so what about this one? -1 to the n, right? Well, this is definitely bounded. This is bounded by -1 and 1. It's bounded below by -1 and bounded above by 1, obviously. What about this one? So this one is bounded below. Bounded below. Ah, so by the way, and so it is bounded. Yeah, it is bounded. So be careful. It's not decreasing, it's not increasing, but it's definitely bounded. This one is bounded below. By what? Actually by 1, right? Or by 0. By 0, for example. And but not bounded above, because it goes to infinity. So you cannot find a capital M which will be bigger than any term. It doesn't exist. It's not bounded above, therefore it's not. It is not bounded. Not bounded, okay? And finally, we get the main theorem of this section concerning sequences, and this is a famous theorem. This is called the monotonic sequence theorem. Monotonic sequence theorem. And it says the following thing. It says that every bounded monotonic sequences or sequence is convergent. So be careful, you have two hypotheses to be satisfied to check that the sequence is convergent. You need to check both that it is bounded and that it is monotonic. And as you can see, both conditions are totally different. Some sequences can be bounded but not monotonic, and some are monotonic but not bounded. So you need to check separately both of them. Let me say a word about the proof of such result. The proof is actually based on the completeness axiom. Axiom is a statement that cannot be proved actually. So it means that this theorem needs also a fundamental hypothesis that we accept, and that is called an axiom. And this axiom is an axiom of completeness of the real number. The completeness axiom of the real numbers. Which basically says the following. So what is it? This axiom says that if S is a non empty set of real numbers that has an upper bound. Yeah, so when it's bounded above by some capital letter M, this capital letter M will be called an upper bound, okay? And the small m will be called a lower bound. So if you take a set of real numbers non-empty, which has an upper bound, so let's say capital M, then S has a least upper bound B. So what do I mean by a least one? I mean that there exists a B. This B will be in S, in my set S, and such that B, first of all, is an upper bound for S, and second, all other upper bounds are bigger than B. So when these two conditions are satisfied, we call such a real number a least upper bound, and somehow we assume that it exists in any non-empty set admitting an upper bound. This cannot be proved actually, but if you use this fact, then you can prove the theorem. And let me show you how we can do that. Proof of the theorem. Okay, so we consider our sequence AN, and it is monotonic, and bounded, right? By hypothesis. It's monotonic and bounded. Then, first of all, monotonic means that it's either increasing or decreasing. Let's assume that AN is increasing. The decreasing case is similar. Increasing. So now, since it is bounded, well, it means that it is bounded above in particular. Okay? So it means that there exists an upper bound M. Right? And now, by the completeness axiom, I know that there exists a least upper bound. This least upper bound, I call it L. And my claim is that this least upper bound is actually the converging limit of AN when n goes to infinity. So it converges, and this limit will be precisely the least upper bound, which exists only by this axiom. which means a fact that cannot be proved actually. So you see, this is same problem happening with mathematics. It is usually based on some fundamental axioms. Okay, how do we prove that AN converges to L? So, proof of the claim. Yeah, we need to show more precisely that for any epsilon greater than 0, there exists some capital N greater than 0, such that if my small n is larger than this capital N, then in such case, AN minus capital L will be less than epsilon. Now we fix the epsilon. Then we can be for sure that L minus epsilon is not an upper bound. This cannot be an upper bound because actually L is the least upper bound. So it's the smallest possible one. So this L minus epsilon is not an upper bound for S, which represents a set of all possible values of AN. Now, to say that it is not an upper bound means that there exists some n, such that if n is large enough, so larger than this capital N, then AN will be actually bigger than L minus epsilon. Okay? So basically this L minus AN will be less than epsilon and will be greater than 0. So this is actually, yeah, so basically we have proved that L minus AN or AN minus L in absolute value is less than epsilon, okay? So this is just what happens if AN is increasing. If it's decreasing, you will use same kind of arguments, except that you will use bounded below by some small m and using again completion of the completion axiom, completeness axiom. Okay. And this theorem will be proved extremely important to study the convergence of sequence as we will see in many exercises. Thank you. I will stop here.